So we're going to talk about formal mathematics or computer-based formal mathematics. So I'll be talking about the mathematical challenges in building a formal mathematical proof for a computer. Like not just the practical challenges of entering it on a computer and so on and so forth, but actually showing that there are some mathematical and conceptual challenges to doing that. Thorsten Altekesh talked on your channel about Lean, I think, the theorem proof of Lean.
If this is the case, then this is the case. So how do I prove an implication?
So people should be already aware by just looking into that or the many other videos on the internet, on YouTube of the appearance of these theorem provers and so on and so forth. Mm-hmm. But I will just here tell you what is the goal of that to remind people, the philosophical or the mathematical or the high-level goal of writing a formal mathematical proof. So you basically want, we'll just write to you a very simple proof, right? If we just say Aristotle is a man, and I will just call that assumption 1, and assumption 2, all men are mortal. Then from those two assumptions, I hope everyone agrees that we can derive that Aristotle is mortal. So when I say formal mathematics, I mean writing down a mathematical proof down to that level of unambiguity. It's crystal clear what we're talking about. There aren't any conceptual leaps, there aren't any logical leaps. It's just as clear as that, right? If you try to write a proof like that, as I said, you can do it to the computer, on Lean, Isabelle, other theorem provers, but the challenge of entering it on a computer is one thing, but there's also a fundamental challenge of translating a proof that is intended for a human to understand into a proof that is as unambiguous as this one. Okay? So there are many challenges with that. Some of them can be just pure tedium, for example, right? It can just be that you have so many symmetric that your proof considers so many symmetric cases and so on and so forth. But some of them are also less tedious and really are just about translating a graphical argument, for example, to a verbal argument. And I will focus on this, having a graphical argument to a verbal one. And you will see in the process what are the challenges of translating informal proofs or some of the challenges of translating informal proofs to formal proofs. So, for example, verbalizing the graphical argument that I will discuss with you now. On the number file, I think there was a video a few years ago on the so-called stable marriage problem.
These two are going to say, to hell with this arrangement and run off together. So that's what we want to avoid.
So this is a very related problem here. Here we have the problem, so-called online matching, right? That's a problem in computer science and economics, mathematical economics, and in operations research called online matching. What is the problem? We quite simply have some sellers, right? So you have S1, S2, S3, S4, 5, and 6. So let's say this one sells t-shirts, shorts, shoes, socks, and so on and so forth. And you have buyers, and every buyer is interested in a few of what the sellers are interested in. But every buyer can only afford one item, and every seller is only selling one item. What that means is that every buyer can only be matched to one seller. So this is one constraint, right? That every buyer can only be matched to one seller, and every seller can only be matched to one buyer. Another constraint is the following in this problem, that the buyers are arriving online. So here we have B1, 2, 3, 4, 5, and 6. So just imagine with me that all of them weren't there, and then only one arrives, B1 arrives, with its preferences, right? So B1, for example, is interested in what S1 is selling and what S3 is selling. The computational problem is the following. When a buyer like that arrives with their preferences, you have to decide immediately for that specific buyer if you're going to grant any of the preferences or not, if, of course, there is an available seller, right? And so we set two constraints, right? So the first one is every buyer can be mapped to one seller, and a seller can be mapped to one buyer, and the buyers arrive online, and you have to decide online whether you will grant their preferences or not, for example. The goal is to match as many buyers to as many sellers. The algorithm we're talking about is an algorithm called ranking. It's due to Karpan, Vazirani, and Vazirani from 1990s. It's a very well-studied algorithm in the theory of computing. So I will just show you how it operates. So this algorithm simply does the following. So as I said, the buyers arrive in order, so B1, 2, and then till 6. So let's say B1 arrives. So firstly, it randomly permutes those sellers, right, before it starts. So I'm here assuming that those S1 to S6 have already been randomly permuted. Once you randomly permute them, you're done with the sellers. You don't do anything there. And then whenever a buyer arrives, you just match it to the topmost available seller in the list of sellers. So for example, for B1, what are its preferences? S1 and S3. So you just simply match it to S1. And then B2 arrives, right? What are its preferences? S1, S2, and S4. So what is the top available seller? It is S2. And then B3, what are its preferences? S1, 2, and 4. Then you will map it to 4. And B4, what are its preferences? It's 1 and 3 is available. So you map it to 3. And buyer 5 arrives, what are its preferences? 4 and 5, you map it to 5. And 6 arrives, what are the preferences? It's just 5, and 5 is not available, so you cannot map it to anything. One of the most important things to understand about this algorithm, if you're trying to mathematically study its behavior, is to know how its output changes if one of the buyers just doesn't show up. What is the difference between when the buyer is there and when the buyer is not there? So if we just assume that buyer 2 will not show up, right? What happens? So then this means that 3 arrives, right? And then seller number 2 is available, right? Because it was not mapped to buyer number 2. So then 2 will be mapped to 3. This 4 will be available, right? That means that buyer number 4 arrives, nothing changes for it because its top preference that is available is still 3, so that's still there. When 5 arrives, buyer 5 arrives, its top available preference is now available 4 because 4 was mapped to 3 and it's no longer mapped to 3, right? And then 6 can also get mapped to 5 because 5 used to be mapped to 5 when buyer 2 was there, and it no longer is mapped to it. So 5 is free. So maybe let me just label the edges that were dropped from the original matching after B2 is no longer there. So to highlight what edges still remain from the previous matching versus what edges have disappeared, I will just use this marker. So this edge remains, this edge is gone, so I'll just use this wiggly line. This edge was introduced, right? This edge was gone, so I'll use this wiggly line again. This edge is still there, and this edge was introduced, this edge was gone. So now, what is the difference between the two behaviors, right? What's the difference between the output in the two cases? The difference between the two matchings is just a sequence of edges, a wiggly and a purely red edge, right? Not this dark, very like this black one, no. So either a wiggly edge that was removed from a previous matching and then replaced by a red one, right? So what is the difference between the two matchings? It simply is a sequence of edges such that one of them belongs to the old matching and one of them belongs to the new one. So you have wiggly, old matching, red, new, wiggly, old, red, new, wiggly, old, red, new. I hope you are convinced that when you will drop B2, each seller will go down to the next available buyer. So you have like this cascading of the matching. So instead of those wiggly lines, you notice all the lines were shifted down a little bit, right? So this is very clear when you do it graphically like that. But if you want to describe it in a computer, for a computer, first of all, I won't even talk about proving that it's always going to be this, the difference is always going to be an alternating path in terms of one path is a member, one edge is a member, or one edge of the matching is a member of the old matching and another is a member in the new one. I won't talk about proving that. I'll just talk about describing the situation and show you how complicated it can be, because what we'll have to do now is basically have this graph that is very easily understandable as a graph. We need to turn it into a verbal one for a computer or for a formal mathematical proof. So I will just try and show you how to do that for this figure or this path that is the difference between the two matchings, and then how complicated that could be, right? What is the difference between the two matchings? As I said, it's like a path like this. Boom, boom, boom. How did this path arise, or what is the description of this path? So you can describe this path by just saying, okay, this is a path that zigzags across the two sides. I'll just say we have as a function zig, right? So this function, in order, so to describe that path, we need to define a function firstly, zig, that takes a buyer and tells you in this path that constitutes the difference between the two matchings, what is the seller on the other side that is matched to that buyer. So zig is simply, it takes a buyer, returns the seller to which takes a buyer B, to which B was matched in the old matching, right? So for every buyer, you will see that in this path that is a difference, we always go from this buyer to the one to S2, right? And then we go back from S2 to S3, and from B3 we go to S4, which is also the original seller to which B3 was matched, and then you go from 4 to 5, and then from 5 you go to 5 again. So every time you're going from this side to that side, you go from a buyer to the seller to which it was originally matching. All right, the other part of this path is if you take a seller, right? So we'll just call this the zag side, so it zigzags. So there's a function that tells you what is the buyer to which a seller is matched, right? This function takes a seller and returns the buyer to which the seller S would be matched after one buyer drops out, after B2 drops out, for example. So after, in our case here, after B2 drops out. Okay, this is just the first part of the description of the path, right? Now we want to also, a computer cannot understand that yet. Why? Because you need to understand, like we have this part there of the definition, which we might want, like if we want to pursue this definition fully, we might want to even elaborate, and I will just start the description of that other part. So the buyer to which S would be matched after B2 drops out. That is not, like in order for you to write something in a formal math proof, it has to be abundantly clear, right? This is like the buyer to which S would be matched after B2 drops out is not very clear. Which one is that? You have to actually unfold that and turn it into something clear again, right? For example, what are the conditions? So this buyer has to be a buyer because for computers it's not always obvious. That other buyer, you will have to then observe how that path is constructed, but that buyer has to arrive after the original buyer to which S was mapped, right? So you will not match S to something that is before B2, for example. Like S2 will have to be matched to something that arrives after it. Of course, that other buyer will have to be interested in what this S is selling, and there isn't any buyer arriving between that new buyer and the old buyer that is interested in what S is selling and that is not matched to something above S. So as you can see, I mean, the point here is not for you to really verify these conditions, but it is to show you the process that when you're trying to describe something like that to a computer, you really need to study a situation that might be very easily explained to a human and then see all of these possible corner cases that you want to avoid. So other than putting the proof in a computer, this is the other consideration that you need to take when you're doing formal proofs. Like you will need, before even touching a computer, you will need to think if your original proof or your original argument or your original situation is at that level of detail or not. And if not, you will have to write down something like this. And a lot of times, in fact, this can be mathematically interesting. This can show you new mathematical ideas when we're writing down these details and exploring all the corner cases. And it can lead to new proofs and even can lead to shorter proofs. So for this specific algorithm, for example, this is a part of work I've done with one of my students, Christoph Madlener. The mathematical study of this algorithm has been done for 6 times at least, right? 3 of those papers just talk about this figure and assume it's so obvious what will happen when you remove a buyer. And that's why like this always reasoning about this figure is just one line. But when we did the proof in a formal mathematical proof, that turns out reasoning about this figure and this graphical part of the reasoning turns out to be almost 40% or 60% of the effort. Like it can just show you that like it can be a completely different proof. So this is something that's basically what I wanted to talk about.
And presumably you can then apply this same thing to different.
Yes, different matching problems.
Matching problems. That's the word I'm looking for.
Yeah. So it's you have to, but I think, as I said, like when you're writing a formal mathematical proof, from equivalent to an informal proof, one part is just tedium of entering something in the computer, and actually we had to go on a whiteboard and study all of these corner cases and what is the actual description of, like it was much more than just the tedium of entering something on a computer. Does that make sense?
Yeah, and often those corner cases and things, that's because you're trying to avoid unintended consequences.
Yes, exactly. Yeah.
I mean, what sorts of consequences could happen if you missed those? The computer makes the wrong assumption, or so a formal mathematical system will usually not. We'll just tell you that this is not a proof, and you will have, and that's how we
actually were first aware of these corner cases, because we firstly thought that this is going to be a very simple part of the product, because in all informal proofs, this is just a one-liner, right? So we thought this is going to be simple, but then we tried to prove it, and the computer just simply didn't accept our proof, because you have to write a proof into these proof assistants, and they check your proof. They don't try to prove it all on their own, right? And they just didn't prove it.
No proof.
Yeah, no proof, exactly. So you have to do that, and it took 4 weeks or so, but yeah, it was rewarding, yeah.
To make it people to understand it is to use these proof systems. Now they have another
not export, but just sent a rubbishy export key for some other reason. Fair enough, right? So the question then becomes, how do we break